Yeah.
The question is whether or not a signaling cell, no, a response cell can become a signaling cell. Not necessarily, because the signaling cell has to be a cell that's able to release a neurotransmitter or able to release a hormone. So those cells have special capabilities that the response cells don't. So typically, no. So the hormone, if a hormone is reaching the target cell, then either you have to break down the hormone or other cells have to take it up. So that happens especially with neurotransmitters. The previous cell recycles the neurotransmitter. But usually you have to break it down. But this cell is not going to take up this hormone and then release it again, because the hormone isn't coming inside the cell, it's just attaching to the receptor on the surface of the cell. Unless it is a steroid hormone, which is a different story. All right, respiration, our next topic. Basically, so far, all you know, unless you're remembering stuff from high school, is that photosynthesis uses carbon dioxide to make sugars, and respiration breaks down sugars and releases carbon dioxide. So, in one case, you're relying on chemical energy being stored in chemical bonds. In the other case, in case of respiration, you're releasing that chemical energy from chemical bonds. So we're going to take a look at the details of this. But we're also going to look at fermentation towards the end of Wednesday. And we practically won't do anything with anaerobic respiration. So there's aerobic respiration where the final electron acceptor is oxygen, and then there's anaerobic respiration where the final electron acceptor is not oxygen. So there's still electron transport. You still do a lot more than fermentation by not using oxygen.
You will come back.
So when people say cellular respiration, they usually mean aerobic respiration. And so aerobic respiration, the simplistic view that you have and you are using in lab as you're designing your respiration experiments is that you take your glucose molecule and you need oxygen, and then you break it down and you release carbon dioxide and water, and you get some energy out of that in the form of ATP and some heat energy also. So that heat is released in the environment. So one of the things that you have to know is the concept of redox reactions, so oxidation and reduction reactions, which are always paired. If something is oxidized, something else has to be reduced. So this is the way that you always have to remember redox, is that if you lose an electron, you're oxidized. If you gain an electron, you're reduced. So we learned it as Leo the German.
We never learned it.
Apparently that's offensive to Germans, and I haven't figured out why. So I apologize to the Germans in the audience, but lose an electron, you oxidize, gain an electron, you reduce. This also works for hydrogen, not protons. If you gain a hydrogen, you're reduced. If you lose a hydrogen, you're oxidized. Because the hydrogen carries an electron, not protons. Protons don't have electrons. So either lose an electron or you lose a hydrogen, you're oxidized. You gain an electron, you gain a hydrogen, you're reduced. You should remember that because redox means oxidation and reduction are always paired. Something that's giving up an electron, something else is picking up the electron. So let's take a look at an example here. Here you have methane being turned into carbon dioxide and water. So methane is oxidized, and the oxygen is actually reduced. So why is it that the methane is oxidized? Both the carbon and the hydrogen are oxidized. Are they gaining electrons or losing electrons? Yes, ma'am. They're not losing electrons or gaining electrons. So why are they oxidized or reduced? Yes, sir. It's the electronegativity of the oxygen compared to carbon and hydrogen. So carbon and hydrogen share electrons practically equally, but if you change the bond so that the carbon is now bound to oxygen as opposed to hydrogen, the electrons are spending more time around the oxygen than they are around the carbon. So that in effect, carbon is losing electrons, even though technically it hasn't lost any electrons. So you have this lovely diagram showing you how the electrons are in the middle of carbon and hydrogen because they're shared equally. But when you have the carbon dioxide and water molecules, the electrons spending more time around the oxygen in both cases, So they're spending less time around the carbon, less time around the hydrogen. So the carbon and hydrogen in methane are, in effect, losing electrons because their electrons are spending more time around the oxygen. And oxygen, that was bound to another oxygen, shared electrons equally. But now that it's bound to carbon and hydrogen, it's gaining electrons because the electrons are spending more time around it compared to the carbon and hydrogen. That's why they're reduced or oxidized, not because they're actually losing or gaining any individual electrons. It's the time the electrons are spending around the nucleus. So, when you look at glucose, same idea, that when you go from carbon and hydrogen bonds to carbon oxygen bonds, you're oxidizing that, whereas the oxygen is becoming reduced. So we're going to take a look at the energy that's being released and harvested by the cells as you start with glucose and you end up with carbon dioxide. And so if you were to burn glucose through combustion, you would release a lot of energy all at once, not terribly useful to a cell. So your cell doesn't do that. Your cell actually breaks it down in steps and harvests the energy in steps. And notice that there's some upward steps. So energy goes up first before it comes down. And we've been talking about those reactions, the energy investment phase as opposed to the energy harvest phase. So these stepwise changes allow your cell to harvest some of the energy and not lose all of it as heat to the environment. So you have to know NAD+, NADH, FAD, and FADH2 as electron carriers, which are used in harvesting energy as you're breaking down glucose, and the fact that they're going to be used to then provide energy for ATP synthesis. So we're going to take a look at the roles of these molecules as we go through the various steps. Right. You also have to know the term ETC, electron transport chain, which is part of the inner membrane of the mitochondria. And this is a bunch of complexes, protein complexes together. Electron transport is not the same as electron transport chain. Electron transport chain is the proteins in the membrane. Electron transport is when electrons are being passed from one complex to the next to the next. And that's a mistake that students normally make when they're answering a question on an exam. They say chain when they actually mean electron transport. So the final electron acceptor in aerobic respiration is oxygen. In anaerobic respiration, you still have electron transport through an electron transport chain, but your final electron acceptor is not oxygen, it's some other molecule. Right. 3 major steps. Well, actually there are 4 technically. There's glycolysis, then you have pyruvate oxidation, oxidative phosphorylation, and there's the citric acid cycle as well. So pyruvate oxidation is usually left out, but it's really distinct from citric acid cycle. So you have to oxidize pyruvate before you can bring carbons into the citric acid cycle. And we're going to talk about that in a little bit of detail. So we're going to start with glycolysis, go through that, take a look at pyruvate oxidation, take a brief look at citric acid cycle, and then look at oxidative phosphorylation on Wednesday. We may get through citric acid cycle today, we'll see. So this overall diagram is showing you where things happen. Glycolysis happens in the cytosol, and you get 2 ATP, net 2 ATP out of that. And there are also 2 NADH molecules that come out of that. Then you have pyruvate oxidation, which releases 2 carbon dioxides for each glucose molecule. And then you have the citric acid cycle, which releases more carbon dioxide, and then you get some FADH and NADH out of that, and you get a little bit of ATP out of that, so 2 ATPs out of that as well. And then you have oxidative phosphorylation in the membrane of the inner membrane of the mitochondria, where you get most of your ATP. So let's take a look at the details now. Glycolysis. You start with one 6-carbon compound, glucose. You end up with 2 3-carbon compounds, pyruvate. No carbon gain, no carbon loss. But in breaking down the glucose into 2 pyruvate molecules, isotite, you do harvest a little bit of energy. So before you can do that, you have to invest some energy. Remember, in that energy diagram, there were steps going up first. So you have to invest energy before you harvest energy. So let's take a look at the reactions here. Here's your energy investment phase. You're using 2 ATP molecules. And then you have your energy harvest phase, where you make 4 ATP molecules. So you lose 2, you gain 4. The net is a net gain of 2 ATP and 2 NADHs per glucose molecule. So you don't get that much out of glycolysis. You just get net 2 ATP molecules into an ADH. And NADH is an electron carrier, high energy electrons that can be used later in electron transport. And I'm going to take a look at that on Wednesday. So let's get into detail. Energy investment, energy goes up, energy harvest, energy comes down. So you start here with your glucose, change in energy level, positive change, and then harvest, negative change. So far, so good? Yes, ma'am.
You said that it uses 2 when it gave 4. Where do the other 2 go? Does it make a change, not a change, but a bond with something else, with oxygen?
I'm sorry, say that one more time.
When it loses 2 to gain 4, is that one?
So you hydrolyze 2 ATP molecules here,
Yeah.
and then later on you make 4 ATP molecules.
So does it have to bind with oxygen or something?
No oxygen involved here. This is glycolysis. This is in the cytoplasm. This is not in the mitochondria. No oxygen involved here.
So how does it create the other 2?
Say that again?
How does it create the other 2?
It's not creating anything. It's through phosphorylation then. This is a phosphorylation reaction. Substrate level phosphorylation, so they gain phosphate from something else. And we're going to take a look at those reactions actually. So here are the reactions. You do not have to memorize these reactions. Like you take biochemistry, you have to memorize these reactions. How many of you are pre-med? You have to take biochemistry. And cats require biochemistry now. But you need organic 1, 2, and lab before you take biochemistry. So there are a few more semesters before you do that. Alright, so let's start with the glucose here. Energy investment phase. You use ATP. You add a phosphate group to the glucose. Then you lose another ATP, add a second phosphate group to fructose here. So there's an isomerization going from fructose 6-phosphate to fructose 6-phosphate. And then you use your second ATP. So you've added 2 phosphate groups. And then you have enzyme aldolase and isomerase so that you get your glyceraldehyde 3-phosphate. So at this point, you have broken it into 2 3-carbon compounds, each of which has 1 phosphate group. Still no energy harvest. In the next few steps, you harvest energy. So each of these glyceraldehyde 3-phosphates then goes through a series of reactions where you have first the redox reaction, NAD+ is reduced to NADH, which means this is now oxidized. So you're going from an aldehyde to a carboxyl group. So an aldehyde is a carbonyl, and now you're going to a carboxyl. So that is an oxidation step. So this is oxidized while NAD+ is reduced, redox reaction. The next reaction, you're going to transfer one of the phosphate groups to an ADP to make ATP. This is called substrate level phosphorylation, which your textbook mentions. So you're not using oxidative phosphorylation like you do in the mitochondria. This is just a transfer of phosphate from one molecule that has phosphates to another molecule that picks up the phosphate. So ADP has 2 phosphates, ATP has 3. You need a phosphate group. This molecule donates a phosphate group there. The next set of reactions, again, you change the shape a little bit, and then you do another substrate level phosphorylation. So the second phosphate group is given up, and you make another ATP here. So far, so good? Yes, sir.
So we take phosphate from ATP to ATP, the phosphorus?
In the first 2 reactions, you take the phosphate from ATP and attach it to the sugar. And then you take some inorganic phosphate and attach it to the sugar. And then you transfer the phosphate from the sugar to ADP to make ATP. All right, so notice the final product is pyruvate. It's a 3-carbon compound. So 1 glucose, 6 carbons, 2 pyruvates, still 6 carbons. So no carbon dioxide production, no oxidation reactions with oxygen itself. So there's no molecular oxygen requirement for glycolysis. Any living cell can basically do glycolysis. But you only get 2 ATP out of that. So the net effect is 2 ATP, 2 ADH. Not much. Most of the energy of glucose is still stored in